Okay, so this is section 5.2. We've already learned about expected value, which is the mean, and variance, which is the square of the standard deviation of a probability distribution. Again, a probability distribution is where you associate a probability to every possible outcome of a random variable. Okay, so just real quick, I've got two populations. One I'm calling X, another I'm calling Y, and they have just four values: 7, 9, 9, and 11, and 1, 2, 2, and 3 for Y. And what we're going to do is just graph the probability distributions. To get a 7, that's a 1 out of 4 probability in the first population. So with a 1 out of 4 probability, that's 25%. Okay, to get a 9, that's 2 out of 4, so that's a 50% chance. And I'm going to make my marker a little darker here. And then to get an 11, there's only 1 out of 4, so that goes down to a 25% chance again. Okay, any questions? Okay, same thing with population 2. The values are a little more spaced out. So to get, sorry, no, these are closer together. To get a 1, again, there's one way to do that out of 4. So 1/4 is 25%. To get a 2, there's 2 of those out of 4, which is 50%. Okay, and to get 3, once again, there's only 1 of those. So the probability is 1 out of 4, so that's 25%. Remember, these are probability distributions. For every outcome, we associate a probability. So for, again, for X, the outcomes were 7, 9, and 11. Probability is 0.25, 0.50, and 0.25. Total, in each case, was 1. Y was 1, 2, and 3 with 0.25, 0.5, and 0.25 probabilities. And again, they add up to 1. Now, next thing I want to do is show you how you can use your calculator to compute these. So real quick, and when I say compute these, I mean the mean. And maybe let's do one mean by hand, just to remind you guys how to do this. Okay, so for X, I'm going to squeeze in right here. I wonder if there's room for that. X, P of X. And over to the right of that, I'm going to do an X squared P of X. Like that. Okay, so 7 times 0.25, maybe I should zoom in on that. Okay, so 7 times 0.25 is 1.75. And 9 times 0.5, I think, is 4.5. And 11 times 0.25, that's 2.75. And when you add those up, you get the mean. So let's do that. This will be, if we do it right, it'll be totally obvious. This comes out as a 9. Okay. So from the graph, clearly the mean is 9. So that's mu. Okay. It's also called the expected value of x. Okay, so we can put that down below here. And let's do the standard deviation and the variance real quick. So for the standard deviation, and maybe over to the side, I'll remind you of the formulas. The mean is the sum of x times p of x. Standard deviation is a little messier. Square root of the sum of x squared p of x minus the mean squared. Okay, so that's how you compute the mean. Sorry, the standard deviation. Okay, so now to do that, x squared on the first row is 49. So you're doing 49 times the probability, which is 0.25. And it's 12.25. And then 9 squared times 0.50 is 40.5. And then 11 squared is 121 times 0.25. So that's 30.25. I'm going to add those up. Okay, anybody get that? I'm going to have you guys computing along with me if you don't mind.
83.
Thank you so much. Okay, so that adds up to 83. Okay. Now let's see, if you just, maybe over to just to kind of up above here, we'll say this was the square root of x squared times p of x. So this is 83 here, minus the mean squared. So the mean was 9 up above. So I don't know if you can see that 9 squared is 81. So the square root of 83 minus 81 is the square root of 2, which is about approximately 1.41. Okay, so the standard deviation is approximately 1.41. Okay, so that's doing it by hand, a little bit tedious, and we won't do that again. The variance is the standard deviation squared. So what's the variance? We know the standard deviation was the square root of 2, right? And you can type it or say it out loud. What's the variance? Two. Okay, we also need the range. So up above the range is the max minus min. So that would be 11 minus 7. Okay, so that has a range of 4. Okay, any questions about that one? Okay, then we're gonna do the same thing for the other variable. Not seeing any questions. Well, I'll just leave it like this for a minute and then I'll zoom in on the other one. I'm trying to figure out how to show you my video with my calculator. Let's see if I do this. Okay, so here's my calculator. This is going to be super choppy, isn't it? Okay, I'm going to do a memory clear. And remember, you press the on and the clear button to do a memory clear. Oops. Try again. Okay. And then in data, the values were 1, 2, and 3. Like that. The probabilities were 0.25. 0.5 and 0.25, like that. Once you've got your data in with the probabilities, and notice the probabilities, another word for probability is a long run relative frequency. So the relative frequencies are in list 2, also known as probabilities. The data values are in list 1, okay? I'm going to press clear. Second time in, you just do second data, so second data. We still only have one variable, so this is one variable statistic still. And the only thing I need to tell it was that I had relative frequencies in list 2. So if you change the frequency thing and say, okay, I had those in list 2, like that, then you can do your computations. Okay, so your mean is 2, okay? And we want this, the population standard deviation. There is no sample standard deviation because this is not a sample. But the population standard deviation is this. So again, the mean is 2. It's using an X bar, but we know this is a population mean, so we're going to call it mu. And the standard deviation down here. So let me jump back to the notes real quick. The mean is the expected value of the variable which we call y, so that's 2. The range is 3 minus 1, which is also 2. Standard deviation was there. If you look, it's 0.7071. But what I'm more interested in this lesson is the variance. So I'm going to show you real quick how you can get a really precise squaring of the standard deviation to make it the variance. So just real quick, where is it? There it is. Okay, so on the screen, I've got the standard deviation here. If I type item 4, it'll paste this on the screen. So I'm just going to press the 4 button and see how it makes the standard deviation symbol on the screen. And you can hit enter if you want to know what the standard deviation is again. But we actually want to square this. So I'm going to press the x squared button to square this. So that's the standard deviation of the variable x squared, which is the variance of x, and it's a half. Okay, and I'll just write that as 0.5. Okay. Okay, so for my other variable, the variance was just 0.5 exactly, no rounding at all there. Okay. So we've described these pretty well. We've got the shape as both of them kind of roughly bell-shaped, high in the middle, low on the ends. The center is the means, so the means mean is 9 for x, and for y, the mean is 2. Okay. We have spread, which are the standard deviations. Also, the variance is a measure of spread. Okay, so we have to do a new population, which is going to be x plus y, and that means every x plus every y. So you have to look at the first value of x. I'm going to zoom out a little bit. The first value of x was a 7. You have to add every y to that. So there's a 7 plus the first y, then the second y, then the third y, then the fourth y to the 7. Okay, so 7 plus 1 is 8. The next y is a 2, so 7 plus 2 is 9. There's another 2, so you get another 9. And then 7 plus 3 is 10. Okay, that's 7 plus all the y values. Then the next x is a 9. So we're going to add all the y values to the first 9. The y's are 1, 2, 2, and 3. So 9 plus 1 is 10. 9 plus 2 is 11. 9 plus the other 2 is another 11. And then 9 plus 3 is 12. Okay. Now there's another 9 here. So we have to do the same thing to the second 9. We add all the y values and you'll get the same as what we just got. 10, 11, 11, and 12. Okay. Now the last x is 11. And we'll add 1, 2, 2, and 3 to 11. So 11 plus 1 is 12. 11 plus 2 is 13. There's another 2, so you get another 13. And then 11 plus 3 is 14. Okay, so that's kind of strange. We have to know what happens when you add two variables together, because there's lots of times in statistics where we add variables together, like when you average values, you add a bunch of values together to average them. And we need to know what that does to the averages when you add values together. Okay, now what I wanted to do real quick here is make sort of a table like this. And it's going to have to be small. So the values go from 8 to 14. 8, 9, 10, 11, 12, 13, and 14. Okay. And there's going to be an x plus y heading and a probability of x plus y. Just note there are 16 outcomes here. Okay, so whatever we do will be divided by 16. So how many times we get an 8? Looks like just 1. So I'm going to say 1 out of 16 here. I'll do kind of a sideways 1/16. Okay. How many times did we get a 9? Well, there's 2 of them. So that'll be 2 out of 16. 10, there are 1, 2, 3 10s. So that's 3 out of 16. Then the 11, notice there are 4 11s. So that's 4 out of 16. Okay. There are 3 12. Are there 3 12s? 1, 2, 3. Okay, so that's going back down now to 3 out of 16. And so it's really important to just sort of notice how these are rising and falling in probability, just like the original variables were rising and falling. We're now going down, falling down to a 13. There's 2 of them, so that's 2 out of 16. And the 14 is only 1 out of 16. So those are our probabilities. Unfortunately, I kind of need to do this in decimal. I know some of these. 4 out of 16 is 0.25. 3 out of 16, I think is, I don't know. 3 out of 16 is an 8, so that's going to be 0.0625, I think. I may as well just do it. So, or maybe that's 1 out of 16. So 1 divided by 16 is 0.0625. And 2 out of 16 would be twice that, I guess. So that's 0.125. 3 out of 16 is 0.1875. And then these repeat. Like that. Okay, so any questions? I'm looking up to see if anyone has questions. Again, this is just a theoretical discussion, but we will use the results of it. Okay, I'm not seeing or hearing any questions. So the next thing I want to do is type these in and get a mean and a standard deviation for the x plus y values. So back to the calculators. Okay, so I'm going to do another memory clear and data and start typing. What did the values go? They went from, 8 to 14, got it. So I'll just start typing the first column. Okay. I don't know if I can remember, but I think the first was 0.0625. And then I hope the next one was 0.1250. Then a 0.1625, I'm not sure. So what was the third one? 1875. So 1875. And then 11, was that 0.25? And then it goes down, 0.1875, then 0.125. Double checking, yep. And then 0.0625. Okay. So that's the whole probability distribution. Every value with a probability associated with it, okay? And then we need the mean and the standard deviation. So I'm going to press clear. Now the mean is going to be mu, but the calculator is going to call it x bar. So you just got to be prepared for that. It's one variable stats. And we have relative frequencies, also known as probabilities, in list 2. Okay, so I'll hit enter. The mean is what they call x bar, but we're going to call mu. The mean is 11, and then we'll go down and deal with the standard deviation in a second. Okay, so the mean is the expected value of x plus y. And before we were saying expected value of x or expected value of y. For the mean, now it's the expected value of x plus y. And I think that came out as 11. The range is the max minus the min, so that would be 14 minus 8, which I hope is 6. And real quick for the standard deviation, back to the camera. So the standard deviation is 1.5811. There. But I want to square that. And you'll see that it's just 5 divided by 2. That's the variance, which is 2.5. Okay, so again, the standard deviation we're going to call 1.5811. When you square that, you get 2.5, and that's called the variance. Standard deviation 1.5811. For variance, we say this is var of x plus y. And I think for the standard deviation, I want to go ahead and use my sigma notation. So this will be sigma for standard deviation, 1.5811. Variance of x plus y turned out to be exactly 2.5. Quick little graph here. So for 11, there's 0.25 right here in the middle. That's another curve. For there's 0.1875 maybe here and here. $1.125. And then 0.0625. So it's not the best graph in the world, but it's okay. And I kind of want to make sure we all see it. It is bell-shaped. Nothing's ever smooth bell. Rarely, anyway. Okay, so that's bell-shaped. All right, I want you to see, can anybody see how the variance is for x plus y? Well, I guess we should start with the mean. So look at the mean for x and the mean for y and see how that's related to the mean for x plus y. How are they related? Anybody?
It's the combined variance of the two.
The means, right? So the 11 for the mean is the 9 plus 2. This is 9 plus 2, which was, we just say it's the expected value or the mean of x plus the expected value or the mean of y. So expected, when you add variables, the means add, which is also, we also say the expected values add. So the expected value of x plus y is the expected value of x plus the expected value of y. Do you see that happening also with the variances? So the variance for x was 2, the variance for y was 0.5, and the variance for x plus y is 2.5, so they add. So the variance of x plus y was var of x plus var of y. The 2.5 was the 2 plus the 0. Well, I'll do it down here. Var of x was 2. Var of y was 0.5. Like that. So the variances add when you add the variables. Okay. And really important also was for x, I wanted this to look like a bell. Not really, but it is sort of bell-shaped. That just means high in the middle and tapers off. Y was a bell, and x plus y is even more of a bell. There's just more outcomes. So again, it's still bell-shaped. That's kind of what we're trying to get out of this. Okay. So I'm looking to see if there are any questions. You can say it out loud or type it. Okay, so sometimes we add variables. We need to know what that happens to the distributions, shape, also the centers. Well, it turns out the means will add if you add the variables. And spread, it turns out that the variances will add if you add the variables. Okay, you see it happening with the ranges as well. So the range for X was 4. The range for Y is 2. The range for X plus Y is 6, which is 4 plus 2. So the variability, whether you measure it with range or with variances, these add when you add the variables. It's not true for the standard deviations though. If you add the standard deviations, they do not add up to the standard deviation for X plus Y. So standard deviation sort of gets pushed off to the side. Mostly we think of standard deviation as being the square root of variance, and variance has really helpful properties. Okay, now down below, the distribution of values for X minus Y. I want to go ahead and I'm just going to do it this way without doing all the gory details of figuring out all the X minus Y's. Just to save time, I'm going to ask you to trust me on some of this. The outcomes are going to be different, but the probabilities are going to come out the same. Okay, so if you do, what's the smallest this could be? X minus Y, the smallest you could get is if you took the smallest X and subtracted the biggest Y, 7 minus 3, okay? So 7 minus 3 is 4. That's the smallest that X minus Y can be. And if you look at the data values, there's only one way to do that, okay? It's the 7 minus 3. There's no other way to get a 4. So that's going to be 1 out of 16. The biggest that X minus Y would come about if you took the 11, the biggest X, and subtracted the smallest Y, which is a 1. So the biggest X minus Y is 10. And that's by taking the biggest X minus the smallest Y. And there's no other way to do that. There's only one way. So that's going to also be a 1 out of 16 probability. The biggest is a 10. Now, the most common thing will be to get a 7. So if you look at the 7s, to get a 7, you could do 9 minus 2, 9 minus 2. And there's 2 2s, so there's another 7. There's another 9 minus the first 2 or the second 2. There's actually 4 ways to get a 7. So the probability would be 4 out of 16. That's in the middle, a 7. And as I said, the probability would be 4 out of 16. So we'll leave that alone. Values are a 5, a 6, the 70, the 7 there, the 8, the 9, or the 10. And that's just how the distribution is going to come out. And so what's interesting with this is you're actually going to get exactly the same distribution of probability. So I can actually just copy this. I know you guys can't, but maybe you could just real roughly sort of draw in this same bell curve because it has the same probabilities. Seems like the distribution will be identical in terms of width, like that. Well, that didn't come out too well. I have to stretch it. That looks good. Heights are wrong. Darn it. All right, fine. I give. I got that in the wrong spot too. You can see the mean. So we won't compute the mean this time. Clearly it's 7. So this would be the mean is, the mean we want to write as the expected value of x. Well, how about this way? Yeah, the expected value of x minus y is 7. And then when you look at the other means for x, the mean was 9 up here. And for y, the mean was 2. So when you subtract the values, the mean's going to be 9 minus 2, which is exactly what we saw in the picture. The mean is 7. That's 9 minus 2, and that's the expected value of x minus the expected value of y. Okay. The range, now this is interesting, the range is 10 minus 4, which is 6. And that kind of brings out the important idea that while the means did subtract when we subtracted the variables, 9 minus 2 is the mean, which is 7, the range is the same as when we added the variables. The range is 6. You see, when we added x plus y, we got 6 for the range. When we did x minus y, we got 6 for the range. So the variability is the same where you add or subtract. And of course, these two graphs are identical in shape. So if you're trying to measure spread, the spread should come out the same for both of these. So for x plus y, the standard deviation is 1.5811. It will also be 1.5811 because they have identical distribution widths. Remember, spread or width is just a measure of how wide the distribution is. They are the same, so the standard deviations come out the same. And the variances will be the same. So the variance of x minus y is the standard deviation squared. Turns out it's going to be 2.5 again, which is the 2 plus the 0.5, and that's the variance of x plus the variance of y. So whether you add or subtract, this is a little confusing, but whether you add variables or subtract them, the variance is add, regardless. Okay, looking for questions. Not seeing any. Okay. Then for one more, let's just zip through this real quick. So for 3y, this is going to be 3, and just to remind you, y had the values 1, 2, 2, and 3. So if you multiply those by 3, you're going to get 3, 6, 6, and 9. Just multiplying by 3. So where is it? Right here. Okay, so 3y is 3, 6, 6, and 9. And let's just say for a 3, that's a 25% chance. There's 2 6s, so that's a 50% chance. And 1 9 out of 4, which is a 25% chance. Like that. We can see the mean. So, oops. So for the mean, this would be mu, and that's going to be the expected value of 3y, which is 12. Nope, sorry, it was 6. Okay, remember the expected value of y going way back up. The expected value of y is 2, right here. When we multiply all the values by 3, the mean becomes 6, which is 2 times 3. So you want to say, oh, the 6 is 3 times 2. And this is 3 times the expected value of y, which was 2. Okay, now I don't want to try and do the standard deviation in my head. So I'm going to go back to my calculator real quick. And see how this works. Okay, data. It was 3, 6, and 9. Okay, and then the probabilities were 0.25, 0.5, and 0.25, like that. Okay, then you press clear. A little choppy here, sorry about the choppiness. Second, data, someone's saying something? I'm doing one variable statistics. And remembering that I have relative frequencies or probabilities in list 2. So the mean is 6, which we...
trading using too much money to concentrate on this.
Somebody needs to mute their mic. So standard deviation is 2.1213 here. And we'll square that real quick. So here's the standard deviation, 2.1213, and then I'm going to press x squared for the standard deviation squared, and that's 9 halves. 9 halves is 4.5. Okay. So let's put those into the handout real quick. Standard deviation is sigma 2.1213. The variance is sigma squared, which is also called var of 3y. And that came out to be 4.5. And now here's the tricky part. Now remember, variance is standard deviation squared. We had to square the standard deviation to get here. How many times bigger is 4.5 times the variance of y? And I'll remind you, the variance of y was 0.5. How many times bigger is it now? You can type it in or say it. It's 9 times bigger. Thank you, Lindy. Okay, so the variance 4.5 is 9 times 0.5. So this is 9 times the expected value of y. So what is the 9 here in relation to the fact that we multiplied by 3? How is that 9 related to the 3? It's squared. Good. So this is 3 squared times the expected value of y. Okay. All right, so we've sort of demonstrated all the principles, certainly not proven them, but we've demonstrated it. And so the first thing is the variables. We want to go ahead and summarize all this stuff. So the first thing was variable x. The center was the expected value of x, that's the mean. The shape was a bell shape. And the spread was the variant, well, we'll just use the variance for that. So var of x. Okay. Then for y, it was the mean was the center, the expected value of y. The shape was also bell-shaped. And the spread was var of y. Okay. Then x plus y. The center is expected value of x plus y, which was, and then I want to go back and remind you, for x plus y, that was the first thing we did here. And we learned that the expected value of x plus y is expected value of x plus the expected value of y. So the means add when you add two variables. So let's put that in down here. This is expected value of x plus the expected value of y. Like that. It was still bell-shaped in terms of the distribution shape, this one. Okay, so we'll just say it's a bell shape. And the spread of x plus y would be the variance of x plus y. And again, we'll remind you for that one, the variance of x plus y was the variance of x plus the variance of y. So the variance is added. Okay, so put that in down here. Okay, then x minus y. Okay, so the center or the mean would be the expected value of x minus y. And just to remind ourselves, going back up here, that was the second thing we did. The expected value of x minus y was the expected value of x minus the expected value of y. So when you subtract two variables, the means subtract. So I would put in expected value of x here minus the expected value of y. But looking at the shape, it was still a bell shape. Okay, so we can say, all right, so that bell-shaped nature is preserved no matter what we did. And then the spread for x minus y, we saw that the histogram was actually the same shape for x minus y as it was for x plus y. And they had exactly the same range. And because the distribution shapes are identical in terms of width, the standard deviation and variance were unchanged from when you added. So unfortunately, as confusing as it is, the variance of x minus y is the same as above. It was the variance of x plus the variance of y. Okay, so that's going to come into play later when we do some discussions that are more theoretical. You add or subtract variables, the variance just gets bigger. Either way, they add. Oh, okay, then kx, well, the mean will be the expected value of kx. Okay. Now, we did do something like that just above. When we had the expected value of 3y, that was 3 times the expected value of y. So the 3 sort of comes out algebraically, and that's what happens here. Expected value of kx is k times the expected value of x. Okay, the shape, still high in the middle, low on the ends here, so we call that a bell shape. And then as far as spread goes, this one was a little more complicated. We were looking at the variance of 3y, and that comes out as 3 squared. I wrote expected value of y. That's a mistake up above. That should be 3 squared variance of y. Please fix that in your notes. And you guys don't ever be shy. I know some of you guys noticed that. Spread can be measured. This is for Nicholas. Spread can be measured in lots of ways. So one way we measured spread was the range, just the max minus the min. Another way we measured spread was standard deviation. Right now, we're measuring spread with variance. Okay, and the main idea is so that, and you have to remember that the standard deviation is the square root of the spread. So the square root of the variance, I should say. So in the end, we're going to use standard deviation. But we'll start with variance always and take the square root to get the standard deviation. Okay. Then going back again, for variance of 3y, that was 3 squared times the variance of y. Oops, hang on. All right, so if you have the variance of kx, this rule says that you have to you can bring the k out, but it comes out squared. So you get a k squared variance of x. Okay, and those are the principles that we need to carry forward whenever we look at a new distribution of some variable. Sometimes we have to bring up these rules to figure out what the mean and the standard deviation are. The standard deviation being the square root of the variance. We'll start with figuring out the mean. We'll figure out the variance, and then from that we'll get the standard deviation. Okay, we've been going for a while. It is 10 o'clock. That means we're going to take our break. I'm going to pause the video. All right, so we're about to begin an experiment, a binomial experiment in section 5.4. And we're going to go to random.org, which is linked in your chat. Okay, the experiment is to drop 4 coins. So if you're using the simulation here, you want to flip 4 coins like that. If you're not using the simulation, then just have 4 coins. And you want to pick a coin that has a clear head and a tail on it. So if you slide, there's so many coins here, and I do not know why they did this, but if you slide way down to the bottom, you can see the US coins. So I'm just going to pick a quarter and 25-cent piece, and then you just say flip coin. And you'll see heads and tails, okay? So I would like to give you a second to do this, please. And then just make note of how many heads you got. I got 1 out of 4. Okay, but let me go back to the Zoom meeting here. Find in the participants tab on the Zoom menu, would you please turn off the check marks? And what I want you to do is if you got 0 heads, give me a green check mark next to your name in the participants tab. Just click the green check mark for a yes. If you got 0 heads. Okay, I don't see anybody. Give me a green, so you don't have to turn those off. Give me a green check mark if you got 1 head. And I did, so I'm going to click my check. Okay, I got 1, 2, 3, 4 of those. So now what we're going to do, we got 4, so go back to your PDF and you're going to do 4 tally marks next to 1 head. 1, 2, 3, 4. And then everybody uncheck yourself. So turn your check mark off. Okay, now some of you others got 2 heads. So give me a green check mark if you got 2 heads. I see Andrea. Nobody else got 2 heads? Okay, so that's 1 person. They got 2 heads. We'll do 1 tally mark next to the 2 on the PDF. Okay, give me, turn that off, Andrea. And then give me a green check mark if you got 3 heads. So I only saw 1 with 3 heads. And give me a green check mark. Turn that off, sorry, Jonathan. Okay, then give me a green check mark if you got 4 heads. We got 1 person, that's Jason. Okay, anybody else? Okay, great. So Jason, clear your check mark. And now we're gonna toss the coins again. So if you look at the window here, oh, I guess let me go back and share what I've done on my iPad real quick. So all you've got on your PDF or your notes is just this outcome. We got 0 people with 0 heads. We got 4 people with 1 head. We got 1 person, they got 2, 3, or 4 heads. Okay, and we're gonna do this for a little while so we can build this up. So real quickly, Let's go back to the simulation. Okay, so go ahead and flip your coins again. Oop. I keep getting 1. Wow, it's like it's broken. All right, well, anyway, so going back to the participants panel, we want to do this as quickly as we can. Raise your hand if you got 1 head. Sorry, 0 heads, bad. Raise your hand if you got 0 heads, all tails. Or give me, I should say, give me a green check mark for that. Nobody, okay? Then if you got 1, give me a green check mark. I just see 1 there. Okay, Winnie, there you go. And now give me a green check if you got 2. Okay, we got 1, 2, 3 there. Plus me. Okay, give me, and turn those off. Green check mark if you got 3. Nick, did you get 3, Nicholas? I guess that's a yes. So we got 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6 tally marks. Okay, everybody turn them off. And did anybody get 4? Okay, I'll take that as a no. Okay, so everybody flip again. Okay, and give me a green check if you got 0 heads. I see 1. Okay, so a tally mark at 0 heads. And then if you got 1 head. Anybody? 1, 2, 3 people. So I'm doing 3 tally marks at 1 head. Okay, clear those. And then give me a check mark if you got 2 heads. Just Alexander? Oh no, there's 2 people. My bad. So there's Alexander, Johnny, and Nicholas. That's 3. Okay, clear those. And then did anybody get 3 heads? Green check mark if you got 3. 1, 2 people. Okay, so and me, so that's all together. Okay, and then 4 heads. Anybody? Clear those. Yeah. 4 heads. Anybody? Okay, I want to do this a couple more times so your patience is appreciated. Go ahead and flip your coin again. So do a reflip. I've just done mine. Raise your hand if you got 0, or I should say, give me a green check if you got 0. Not seeing anybody. Should I wait? I'll wait just another sec. Okay, give me a green check if you got 1. I see 2 and I got 1, so that would be 3 people. 1, 2, 3. Okay, if you got 2, give me, clear yours, everybody. Yep, and green check if you got a 2. 1, 2. Anybody else? Green check if you got a 2. Looks like those are clear already. I saw there was 2, wasn't there? Somebody else had a check that's cleared. Oh, there it is. Okay, so there's 2 of those. 1, 2. And then if you got a 3, a green check. Clear your checks. Okay, 1, 2, 3 of those. 3 is real popular right now. Okay, clear your checks. And then if you got a 4. Did anybody get a 4? We got 1. That's Wendy. Wendy, you got a 4, I think. Okay. Clear them. And we're going to do it again. So flip again. Give me a check if you got 0. Looks like Nicholas did, so that's 1. Give me a check if you got a 1. I see 1 of those. Give me a check if you got a 2. Clear that. Yeah, there you go. Wendy, you got a 2, I gather. 1, 2, 3, 4, and I got 1 also. 1, 2, 3, 4, 5 altogether for a 2. Okay, give me clear those. Give me a check. Jonathan, do you mean to clear those, or are you a 3? Okay, gotcha. Give me a check if you got a 3. Just see 2 of those. Okay, and give me a check if you got a 4. Clear and yeah, and anybody get a 4? Looks like we got 1. Okay. Could we do, I know this is getting a little old, but could we do it one more time? So go ahead and do a flip. I got 3 that time, yay. Okay, give me a green check if you got 0 heads. I don't see any. Okay, so we'll call that a 0. Give me a check if you got a 1. So that's Jason and Johnny. Got a 1, so that's 2 of you. Okay, give me a check if you got a, so we clear? Yep. Give me a check if you got a 2. 1, 2, 3, 4. Wow. Okay, 1, 2, 3, 4, 5, 6. Wow. Okay, 1, 2, 3, 4, 5, 6 tally marks. Okay, give me a check if you got a 3. Anybody? 2 of them? Just 2. How about that? Okay, just 2 tallies. 1, 2. And then finally, let's do, anybody get a 4? Nicholas, you got a 4? Oh, he says no. Bren, you got a 4? Okay, we'll put a tally mark down for Bren. Okay, I think that's good enough. So let me share my results. I'm hoping we all got the same thing. Okay, so that's what I got for my tally. And of course, it's pretty close to what we were hoping to see, a bell-shaped distribution. So the frequencies were 2, 14, what is that, 21, 17, and then 4. So it's not a perfectly symmetric distribution. It's pretty good. Let's get a total here. So 16 and 21 is 37. 44, 54. I got 58. I'm going to double check that. Yeah. Okay, so the relative frequencies would be 2 out of 58 and so on. And then we do want to do these in decimal. And this is one of the cases where I think it's okay to do just 2 places after the decimal. It just gets so messy if you have to graph it. So I'm just going to round to 2 places on this. So 2 divided by 58 is a 0.03. I'm just going to go with a 0.03. And then so on. 14 divided by 58 is 0.24. 0.36. 0.29. This one's a little wacky, 0.07. A little too big. And so remember, it's the long run relative frequency that approaches the probability. Now it's asking for the mean here, which is going to be off by a little bit. But I think what we'll do for the mean, and this is an estimate here, because it's based on just a short run. And we'll estimate the standard deviation. Okay, and then I'm gonna have to pop over to my calculator real quick. So beg your indulgence momentarily while I key all this in. And I guess I have to do a memory clear. And the outcomes were 0 through 4. Does somebody have audio? I'm just going to use the frequencies, not the relative frequencies, because that'll be more precise. Does somebody have audio that can read to me how many times we got 0? It was 2, right? And then somebody, can you tell me how many times we got a 1 with audio? All right,
There's 2 zeros.
Okay, and how many 1s?
14.
Thank you. 2s?
21.
Thank you. 3s?
17.
Good, and there were 4 4s, right?
Yes.
Thank you. All right, so you can use frequencies or relative frequencies when you get your mean and your standard deviation. I'm going to press clear, and then second, data, 1 variable statistics. I have frequencies in list 2. And so my mean is 2. I'm just going to say that's 2.1 for my mean. And from, I guess I should use it. I don't know which standard deviation. I'm going to use the sample standard deviation, even though I'm trying to estimate a population standard deviation. The sample standard deviation is an estimate when you use sample data, which is what we're doing right now. So I'm just going to say it's 2.1 and 0.97, which is approximately 1. Okay? So back to the sheet here. All right, so the mean, and I'm not going to write mu here. I'm just going to write mean is, what did I say, 2.1? Standard deviation is 1.0 when you round it. Yep. Okay, and then the relative frequencies in a graph. So we had a 0.03, down here-ish, hang on. .03, next one was 0.24. Next one was 0.36. Next one, 0.29. Then a 0.07. Nice sort of a bell shape. And I can put those numbers on there, I guess. Okay, any questions? Let me look at my, oh, I have some comments in the chat. Let's see how that comes out here. Oh, put a separate video on how to use the calculator on Canvas, please. Sure, for sure. I'll do that later today. Okay. Any questions? Okay, going on. What we want to do is, so we've got these outcomes, 24%, 36%, and so on. What we want to do is to show that we can use the theory that we've developed to show how these outcomes would have happened, even, roughly, even before doing the experiment. So I want to go ahead and do this. First of all, some notation. This NCX notation, we read N choose X. Okay, so this is the number of ways to choose X successes from N trials. Number of ways. Let's say from N trials. To choose X successes. Now remember, we've got 4 trials. Those are the 4 coins. And any number of successes, you could have 0, and a success is a head. Okay, so S for success is heads. Okay, N is the number of trials, which was 4. Okay, and again, we got any number of successes from 0 to 4. Now this is saying down below, we want to compute the probability of getting 2 successes, that is 2 successes in 4 trials. Okay. Now we're going to do this the old-fashioned way using probability rules. Okay, the probability of getting 2 heads, I'm actually going to list all of the ways you can get 2 heads. So I'm going to call them successes and fails. Okay, so to get 2 heads, you could get 2 successes and 2 fails. But that's not the only way to get 2 heads. There's 4 coins, and there's all kinds of different ways that this can come out. So 2 successes, 2 fails, you could do success, fail, or success, fail, fail, success. Or how about this? Fail, success, fail, success. Or fail, fail, success, success. Or anybody want to list the one I missed? Dylan, you're asking me if this is going to be posted. Yes, I will always post my lectures on YouTube. It'll take a day probably. Fail, success, success, fail, correct. Thank you. Okay, so there's 6 ways to do this. Now, the addition rule says or becomes add. We are going to change these to little plus signs and do individual probabilities. So this is the probability of 2 successes and 2 failures, plus the probability of a success, a fail, a success, a fail, and so on. Okay, so we're adding all of those. Now, when we say 2 successes and 2 fails, you can multiply those probabilities. So just to remind you, little p is the probability of a success. I'm writing up above, okay? Little q is the probability of a fail. Okay, and what I'm doing is I'm referring to what we did earlier up here, where you have the p and the q. Okay, probability of a success and a probability of a fail. So every time it says probability of success, that's going to be a p, and the probability of a fail is a q. And you have this thing called the multiplication rule. It says if the events are independent, the probability of A and B is the probability of A times the probability of B. So I get to multiply with, when multiple things happen, I get to multiply their probabilities. Well, I have 4 coins. If I get 2 successes and 2 fails, then I get to multiply their probabilities. Success, the probability is P. Fail, the probability is Q. These are little p's, not capital P's. And of course, the main thing to notice is that these are all the same. The order is different, but multiplication order doesn't matter. So what you have in the end is 1, 2, 3, 4, 5, 6 different ways for this to happen. P to the second and Q to the second. Now what I actually want to do is I'm going to sort of center this and really kind of highlight everything that's going on. Okay, so the first thing is that the 6 here is the number of ways that you can get 2 successes in 4 trials. Okay. we listed all the ways. There were 6 different ways to do it. Okay, and if you go back up, the ways to get 2 successes in 4 trials, look at this n choose x definitions. Okay, that's the number of ways from n trials to get x successes, n choose x. Well, we've got 4 trials and 2 successes, so this should be 4 choose 2. So the 6 is 4 choose 2. Okay, now the little p here is the probability of a success. Okay, the 2 here, we're raising it to the 2nd power because there are 2 successes. So x is the number of successes. X is 2, the number of successes. Okay, then there's a q, because q is the probability of failure. Okay, the 2 here is the number of failures. 2 heads, 2 tails, 2 successes, 2 failures. Now, the number of failures doesn't have a variable for it. Okay, just to go back up to the top here, n is the number of trials, x is the number of successes, so n minus x is the number of failures. Just subtract the number of successes. Okay, so going back down here, 4 trials minus 2 successes, that's n minus x, is the number of failures. Okay. The only thing I would add to this is to this statement here with the 4 choose 2. Remember, n is 4, and you're choosing out 2 successes, but x is the number of successes, so it's n choose x. Okay, now we can do this computation, so I'm going to switch colors here back to green, I guess. So this is 6 times p, that's the probability of getting heads, and I think that's 0.5 to the 2nd. And times q, that's the probability of a fail, which is tails. Well, tails should also be 0.5, also to the 2nd. And then I just do this on my calculator. So you've got a 6 times 0.5 squared, which is 0.25, times the same thing, 0.25. So that comes out 0.375. Okay, I just want to pause for a second.
Where did you get the 0.5 from?
On the probability, and I didn't put this down, but I'm going to go ahead and write up above this for P of S and P of probability of success and probability of failure. So for a success, that's getting heads, and there's one way to get heads out of 2 outcomes. A half is the probability of getting heads, which is 0.5. How's that?
That makes sense. Thank you.
Good. And tails is the same way. So this is also a half, but remember tails is 1 minus the probability of heads. So this is also 0.5. Thanks for asking. Now, if you just look at what we did, we had the 6, which is 4 choose 2. That's NCX. Then the P to the second, but that was P to the X. And then the Q to the second is Q. 2 was the number of failures, which is N minus X. 4 minus 2. Okay, so I'm just pulling down the elements that we had done up here. Like that. And that's the formula for the binomial probabilities. The only thing that's tricky here was that 6. There were 6 ways to get 2 heads when you drop 4 coins. And that's not something that's easy to figure out. We listed them. And again, not exactly obvious that it was 6. If you were dropping 10 coins and I said, how many ways are there to get 4 successes? To list that it would just take forever. So you really don't want to do that. There is a clever formula for figuring this out. Remember, you're figuring out the N choose X. From N trials, how many ways are there to get X successes? Well, N choose X has a formula. It's N factorial, and I'll remind you what a factorial is in a second. It's N factorial. Factorials have an exclamation point after them. Over X factorial. N is the number of trials. X is the number of successes. And then you also have to divide by the number of failures, which is N minus X with a factorial. Okay. And just factorials, you just multiply the number times the number minus 1 times the number minus 2 all the way down to 1. So if you do 5 factorial, this is just 5 times 4 times 3 times 2 times 1. And 4 factorial, and by the way, that's 5 times 4 is 20 times 3 is 60 times 2 is 120. Okay, 4 factorial is 4 times 3 times 2 times 1. So 4 times 3 is 12 times 2 is 24. 3 factorial is 3 times 2 times 1, which is 6. 2 factorial is 2 times 1, so that's just 2. And 1 factorial is just 1. And then the craziest thing, and I cannot, well, I could very quickly tell you why 0 factorial is always 1. Factorials tell you how many different ways there are to order a group. So if you had 3 things, there are 3 individuals. How many ways can you order 3 things? The answer is 6. How many ways to order 2 things? There are 2 of them. You could do A, B, or B, A. That's 2 different ways to order 2 things. If you only have 1 thing, there's only 1 way to order it. And if you have 0 things, how many ways can you order nothing? 1 way. You don't do a thing. So 0 factorial is 1 essentially because there's exactly 1 way to do nothing. And so we keep that there because of the meaning that I just described. Now, if you want to use, to compute 4 choose 2, you would do this. 4 choose 2 is 4 factorial over 2 factorial. That's the number of trials on top, the number of successes, and the number of failures, 4 minus 2 factorial. So 4 factorial on top, you have a 2 factorial and another 2 factorial in the bottom. 4 factorial, as you know, is 4 times 3 times 2 times 1, which is 24, over 2 factorial times 2 factorial. 2 times 2 is 4. Okay, 24 over 4 is 6. And remember, we knew that 6 up above here was the number of ways to get 2 successes in 4 trials. So we already knew what 4 choose 2 is, but we've just shown how the formula works here. Okay, so now we can kind of quickly zip through some of this. So P is 0.5 for coin tossing experiment. That's 50% chance of heads. Q is 1 minus P, which is also 0.5. That's 50% chance of getting tails. We already did the formula above when we did the probability of 2 successes. This is 4 choose 2, P to the second, and Q to the 4 minus 2. So 4 choose 2 was 6. P was 6 times 0.5 to the second. Q is 0.5. That's also to the second, or 4 minus 2 if you like. And I think that came out to be 0.375. So we don't have to do that again. We already did that. We want to take a moment and develop a formula for the mean and the standard deviation for X, which is the number of heads. And you can kind of guess what the mean is, just looking at the graph, that the average number of heads is 2. And in our trials, we got 2.1. So effectively it's 2. Standard deviation came out to be about 1. We would like a way to theoretically predict the mean and the standard deviation. So I'm about to do a theoretical development. And it's easiest to prove the mean and the standard deviation by looking at the simplest possible case. And so we're going to do the binomial experiment again, but with just one trial. Okay, X is going to be the number of successes. If you're only tossing one coin, you can either get 0 heads or 1 head. So those are the outcomes. X can be 0 or 1 successes. Okay, so tossing a coin, the probability of 0 successes, that means you got to fail. And the probability of a fail is Q. Okay. 1 success means you got heads. A success has a probability that's P. Okay, totals, well, P and Q have to add up to 1. Now, to do a mean, you have to do mean, also called expected value of X. This is a capital X. We're using a capital X right now when we only have one trial. Capital X is the number of successes, the number of heads when you drop one coin. Okay, so the mean is always the sum of X times P of X. Okay, so if I add another column, X times P of X here, I would just multiply. So 0 times Q is 0 in the first row. And 1 times P is P in the second row. And when you add those up, you get 0 plus P, which is P. So the mean is actually the sum of X times P of X, which we just did, this thing, sum of X times P of X here is P. So the mean is P. Now, the standard deviation, just a little more complicated. Sigma is the square root of the sum of x squared p of x, again, that's a capital X, minus the mean squared. So that's the formula we developed last time for the mean and the standard deviation of a probability distribution. All right, well, I have to do the sum of x squared p of x. So let's add an x square p of x column to our table. And so now here, you're doing 0 squared times q, which once again is 0. And then in the next row, x is 1, and p of x is p. So this is going to be 1 squared times p, which is going to be p. And once again, you're adding 0 plus p to get p. So same numbers. And that p is the sum of x squared times p of x. So when you put those sums in for the standard deviation, the sum of x squared p of x was just p, like that. And then we're subtracting the square of the mean. The mean is also p, so you're subtracting p squared here. And that's a little large, so I'm just gonna shrink this down a little bit. So this is the square root of p minus p squared, which we're going to factor as p times so how do you factor a p away from p minus p squared? What do you get? One minus p. Good, thank you, Wendy. P times 1 minus p. And while you're at it, what's 1 minus p? There's a letter for that. Yeah, that was q. Thanks, Wendy, again. So the standard deviation is the square root of p times q. Strange. Remember, the variance is the standard deviation squared. So var of x is sigma squared. So you just take if you square a square root, it just goes away. So this will just be p times q. Okay, so that was the mean and the variance for the number of heads when you drop one coin. Okay, so remember, big X is the number of heads when you drop one coin. Now, going down here, it says when there are n trials, we can think of this as conducting n experiments with one trial each, which is to say, if you drop 4 coins, that's like doing the experiment with one coin 4 times. So little x is going to be the sum of the heads on each individual coin. The number of heads on one coin is big X. So little x is the sum of big X. Okay. The mean of number of heads is the sum, is the expected value on little x. Remember, the expected value on little x is the expected value of the sum of big X, where big X is the sum of the coins, the sum of the number of heads on each individual coin. But then I would remind you that the expected value of x plus y is the expected value of x plus the expected value of y from our last section that we covered. So that is to say, the expected value of a sum is the sum of the expected values for each individual coin. That should be a capital X there. So we're just going to add up the expected value for each coin if you drop a bunch of coins. So the expected value for each coin is P, and there are N trials. So if you're going to do the expected value of P for every trial, but you do it N times, you have to add that together N times, or just multiply by N. So the mean is going to be N times P. That's the mean when you drop a bunch of coins, the mean number of heads. Sigma squared is the variance. You remember that the variance of a sum, so if you had the variance of x plus y, I'll put this up above, variance of x plus y is variance of x plus the variance of y. Okay, so we're doing the variance of the sum of the number of heads on each individual coin. The sum of the number of heads, X, big X is the number of heads on one coin, and we're adding that up for each coin. Sum of the variance is, sorry, the variance of the sum is the sum of the variances for each individual coin. If you go back, the variances are all P times Q, and there are N of them. Okay? Each time you do the experiment, the variance is PQ. You're doing the experiment N times, and the variances will add, so it's N times PQ. Because you're doing it N times. Now, as I said, when we develop a formula like this, we start with the variance and then we go back to standard deviation, which is the square root of variance. So the standard deviation is the square root of the variance for the number of heads, and the variance is NPQ, so the standard deviation is the square root of NPQ. Just like that. So when we do the coin tossing experiment with 4 tosses, the mean is the expected value of X. Formula is just NP. So we tossed 4 coins with a 50% chance of heads. 4 times 0.5 is 2. On average, we should get 2 heads. That's a theoretical average. And it should be what you get if you do this many, many, many times. Okay? If you do it many, many, many times, the mean should effectively become 2. Now going back, we did it, how many times? 58 times, which is a lot. Okay, and the mean was not 2, it was 2.1 up here. We got a 2.1. Keep in mind, we got a standard deviation of 1. So the mean, if we had continued, would get closer and closer to 2 over time. And the standard deviation, well, let's see what it should get close to. We got 1 here. What should we have gotten? Well, the formula says that the standard deviation is the square root of NPQ. N was 4, that's the number of trials. So 4, P is 0.5, Q is 0.5. So 4 times 0.5 is 2, 2 times 0.5 is 1. So this is the square root of 1, which is 1, and that's exactly the standard deviation that we got when we were tossing the coins. Okay, now this is asking down below to do the probability distribution for all values of x. So just to remind you that this is a theoretical distribution, not the practical one that we did with relative frequencies. Okay, so the theoretical probabilities, P of x, came from this formula, n choose x, p to the x, q to the n minus x was the formula we came up with. And it's asking us to fill in those probabilities for every outcome in the table. So we could get, now remember, x is the number of heads when you drop 4 coins. So you could do 0, 1, 2, 3, or 4 heads. We did compute the probability of 2 heads. So if you go back, where was it? Right here, up above. We did 2 heads there, and we got 0.375. So we can just fill that. That was with the theoretical formula, so we'll put in a 0.375 down here for 2 heads. Let's do this again for 3 heads. I don't want to make us do all of this, but let's do the probability that x is 3. So this would be, the formula is over on the left. Remember, n is 4, so it's going to be 4 choose 3. And then p to the x, p is 0.5 to the x, which is 3. And then q is also 0.5, but that's to the n minus x, and n is 4, so it's 4 minus 3, like that. Just a real quick comment on n choose x. On you, if you have the TI-36X Pro, you type in, then you press the, there's a button where the N with an NCR on it. You have to tap that twice, I think. And then you put in the X. Okay, so let me clean that up a little. So I'm going to show you how to do that real quick. Okay, so I'm clearing this. Just the NCR button, this button shares 3 functions that I'm pointing at. Uh-oh, it's a little blurry. Hang on, we'll wait till this comes in. Okay, so I'm pointing to this button here. Looks like the video is really choppy. Okay, so I don't think the video is going to catch up. So I'm going to do this just by writing it down in the notes. Yeah, it's going real slow. Zoom is burdened. So for the 4 choose 3, now all I know, I'm just looking at my video of what I was doing, and I'm waiting for the iPad to go back to the notes again. So it looks like we're hung up a little bit. That was asking almost too much, I think. So I'm just going to pause for a minute. Okay, so for the 4, choose 3. You press the 4. You press that button that has the NCR on it. You have to press that button 2 times. Then you put the 3 in and you hit enter. Okay. So that's a real quick and clever way to get that. And in the end, the 4, choose 3 just comes out to be 4, I think. And then it's times 0.5 to the 3rd times 0.5 to the 1st. Okay. So I see the video's hung up again. Nick Corona, anyone else that has the TI-30 XS? Put the 4 in. You have a button called prob, P-R-O-B, for probability. Put the 4 in, press the probability button, and then choose the NCR. Then put the 3 in and hit enter. Tell me if that works. At this point, I don't even know if you guys can hear me. I'm going to pause the recording. Okay, so I filled in the rest of the probabilities, and those are all computed with the same formula. And I want to go ahead and make this probability distribution now. Okay, so that's the outcome. I'll go ahead and put my probabilities on here. Like that. And we're meant to compare the theoretical development to the one where we actually did it with real coins, or at least a simulated coin. So way up at the beginning, you see the 24% versus the 25%, the 36% versus the 37.5%, the 7% versus the 0.0625. So these probabilities are quite close, not perfect, to what's predicted by the theory. But remember, the theory doesn't predict short range outcomes. The theory predicts long run outcomes. So it's asking, how does the theoretical distribution compare to a distribution of relative frequencies that we did with our real data? And I would just say they are very close. So the theory predicts what actually happened. Pretty closely. And just to remind you again, more trials would give better predictions. I should say, more trials would align with predictions better. And this is just a really important point, that in certain types of experiments, you can kind of predict what will happen, not in short run, but in the long run. And so when we look at data from, millions or thousands of individuals that are surveyed, if we know a few basic facts about the population you're surveying from, you can do a pretty good job of describing how things will come out, not with individuals, but overall. Okay, and that's just sort of a really important and powerful point that we use and we exploit a lot in research using probability. Okay, I'm going to pause and see if anyone has questions. Okay, I don't see any questions. So I think we're good to keep going. Okay, so the next part here is on binomial experiments still, but now we're going to look at a president's approval rating. So it says if a presidential candidate has a 43% approval rating, what's the probability she would get 4 approvals in a random sample of 10 voters? Okay, so N is the number of trials. I'm looking for you guys to tell me how many trials there are in this experiment. You can type it or say it out loud. 10, good. N is 10. Okay, X is the number of successes. How many successes? Good. Now, little p is the probability of success. Okay. Probability of success is the same thing as the proportion from the population. So what's the probability of success? When you pick one person, what's the probability that you'll get an approval? Right, it's 0.43. That's the same as the population proportion. And of course, Q is always 1 minus P. So if 43% of the population approves, then 57% don't approve. Any questions? Okay, and I think that's everything we need to do this. The probability that X is 4 is the question, 4 approvals. The formula says N choose X, P to the X, Q to the N minus X. Okay, so N is 10. We're choosing from 10 trials 4 successes. P again is 0.43 to the X, X is 4, times Q, which is 0.57 to the N minus X, that's 10 minus 4. Okay, off to the side, you want to do 10 choose 4. So 10 choose 4. You put in the 10, execute the NCR function on your calculator. And that's usually by pressing that button twice or going into the probability menu. And then 4, what do you get? Someone besides Wendy. She's doing all the work. Thanks, Nicholas. So there's 210 ways to get 4 yeses out of 10 voters. And if you didn't have this tool, you'd be counting, and that'd just be ridiculous. So anyway, there's 210 ways to do it. Each individual way, the probability is 43% to the fourth power because you need 4 of those. And those are approvals. And 0.57 to the 6th power, because if there are 4 approvals, there have to be 6 non-approvals with a 57% for each one of them. So you just kind of pound this out on your calculator. There's an exponent button and an x to the blank button on your calculator. That's how you raise to a power. 210 times 0.43 to the 4th, and leave the exponent times 0.57 to the 6th. Anyone feels brave? Give me 3 places after the decimal. We don't count leading zeros on probability, so I want 3 significant digits. 0 point something.
240.
Yeah, that's it. That's it. 246.246 is the right answer. So that's 24.6% chance of getting 4 approvals from a random sample of 10 voters when there's a 43% approval rate. Okay, I'm gonna wait and see if anyone has questions. Nicholas, you okay? I'm not sure where that answer came from. I'd show you my calculator, but I'm really nervous because the video just died. Okay, so you got it straight then? Oh, I see, yeah, that makes sense. Okay, cool. All right, so just to remind you, the mean, we came up with a formula, was n times p. This is for a binomial experiment only, and the standard deviation is the square root of npq. Okay, these are for this new type of problem, binomial experiments only. Don't use these on something else. Again, none of this is going to be on your test. Okay, not till the second exam. Anyway, n was 10 here. P was 0.43. So on average, you expect 4.3 approvals. Of course, you're not going to get 4.3 approvals, but that's the center of the distribution. Standard deviation is the average distance from the mean. So here's square root of NPQ, that's 10 times 0.43 times 0.57, like that. Again, this is only for binomial experiments. And let's do 1 place after the decimal. I mean, it's 1.57, which you could round to 1.56. Just to remind you, with means, you carry 1 more digit than the data have. This, the data would be the number of successes, which is a whole number. So your mean should have at least 1 more place than that. So you should have at least 1 place after the decimal on the mean and the standard deviation. Okay, so just this is a great place. Probabilities in percents. This is just a reminder from what we talked about last time. You have to do 3 significant figures. Okay, means and standard deviations. you have to do one place more than the sample data, than just the data, let's say. One place more than the data values. And data values are always denoted by an X. So the values we're averaging are the number of approvals, and the number of approvals is a whole number. So your mean should have one place more than 0 places after the decimal. So you should have one place after the decimal, at least. You could do 2 if you want. And I screwed up, didn't I? So I rounded to 1.5, and of course that should have been 1.6. Okay, so it's 11:37, so that's all we're getting in today. Don't forget your test next week.